Most people think gold is found by luck, a pan in the water, a shiny flake at the right moment, a story passed down about a river that once paid well. But professional geologists know something very different. Gold does not appear randomly. It follows rules. It obeys structure. And long before a single nugget is pulled from the ground, its location is already hinted at on a geological map. A geological map is not just colored paper. To an untrained eye, it looks like an abstract painting of reds, greens, yellows, and lines that mean nothing. But to someone who understands how Earth forms metals, that map quietly predicts where gold can exist, where it cannot exist, and where it almost certainly does exist, even if no one has found it yet. Gold is not scattered evenly through the crust. It is concentrated by heat, pressure, chemistry, and time. And every one of those forces leaves behind evidence. That evidence is recorded layer by layer, fault by fault, intrusion by intrusion. Geological maps are not guesses. They are records of ancient processes that move gold from deep magma chambers into fractures, veins, and eventually into rivers and soils. To understand how a geological map predicts gold, you must first understand one simple truth. Gold rarely forms where it is found. It forms deep, often miles underground, carried by hot fluids released from cooling magma or metamorphic reactions. These fluids move upward through cracks in the crust, dissolving metals like gold, silver, and copper. When conditions change, when temperature drops or chemistry shifts, gold falls out of solution and locks itself into rock. This means gold is not just about rock type. It is about pathways. Geological maps reveal those pathways. When geologists search for gold, they are not asking, where is the gold? They are asking, where could gold have traveled, and where would it have stopped? Fault lines on a map are not just breaks in rock. They are highways. Ancient fractures allowed mineral-rich fluids to rise. The longer a fault was active, the more opportunity gold had to move through it. On a geological map, these faults appear as thin lines, often ignored by amateurs. But when multiple faults intersect, especially near certain rock types, those intersections become prime targets. Then there are intrusive rocks: granite, diorite, tonalite. These are not just names. They are fingerprints of magma that once rose from deep within the earth. Many of the world's richest gold deposits are genetically linked to intrusive bodies, not because gold is in the granite itself, but because the intrusions supplied the heat and fluids needed to mobilize gold. On a geological map, intrusive bodies often appear as large, irregular shapes cutting across older rocks. Where these intrusions meet surrounding rocks, especially reactive ones like limestone or certain metamorphic units, gold deposition becomes far more likely. These contact zones are some of the most productive gold environments on Earth. But gold does not stop there. Over millions of years, erosion takes over. Mountains wear down. Veins break apart. Gold, being heavy and chemically stable, survives the journey. It moves downhill, grain by grain, flake by flake, until it reaches rivers. This is where geological maps continue to matter. Rivers that cross gold-bearing bedrock are fundamentally different from rivers that do not. A map can show which drainage systems cut through favorable geology. If a river never touches the right rock types or structures upstream, it will never carry gold, no matter how beautiful it looks. Professional prospectors do not pan random rivers. They trace watersheds backward on geological maps. They follow streams uphill until they intersect fault zones, intrusive contacts, or metamorphic belts known to host gold. Only then does fieldwork begin. One of the most powerful yet overlooked elements on a geological map is rock age. Gold deposition is not equally likely in all geologic periods. Certain eras were far more productive due to global tectonic conditions. Greenstone belts, for example, are ancient volcanic sedimentary sequences that formed billions of years ago. They are responsible for some of the largest gold camps on Earth. On a map, greenstone belts stand out clearly once you know what to look for. They often appear as elongated zones of metamorphosed volcanic rock surrounded by granitic terrain. These belts host shear zones, another key gold indicator. Shear zones are areas where rocks have been intensely deformed, creating endless microfractures that trap gold-bearing fluids. The map does not say gold here in words, it says it in patterns. Another critical element is alteration. Gold rarely travels alone. It is accompanied by chemical changes in the surrounding rock. Silicification, iron staining, carbonate alteration, and sulfide minerals all leave signatures that geologists can recognize. Geological maps often include alteration zones or are paired with geochemical overlays that highlight these changes. When alteration halos align with structural features in favorable rock units, the probability of gold increases dramatically. This is how professionals narrow down vast regions into specific targets. And then there is scale. Large-scale maps show regional trends, belts, and terrains. Small-scale maps reveal individual faults, veins, and contacts. Gold exploration always begins large and moves small. The map tells you where not to waste time. What makes this approach so powerful is that it removes guesswork. You are no longer searching blindly. You are testing a hypothesis built on Earth's own history. This is why experienced geologists can walk into unfamiliar terrain and identify gold potential within hours, sometimes minutes. They read the landscape the same way a doctor reads an X-ray. The hills, the rock colors, the stream directions, and the fractures all confirm what the map already suggested. Even modern gold discoveries still rely on these principles. Satellites, geophysics, and drilling all start with geological interpretation. Without the map, none of the advanced tools know where to look. And perhaps the most important realization is this: geological maps do not become obsolete. Gold does not move back uphill. The processes that formed deposits ended millions of years ago. The clues remain fixed in stone, which means that even today, with the right understanding, the map can still lead you to gold that has never been touched. And this is where most people make a critical mistake. They look at the map but do not know what combinations matter. They focus on a single feature instead of convergence. Gold almost never forms from one factor alone. It requires alignment. Rock type, structure, heat source, fluid pathway, and timing must all intersect. When three specific geological elements appear together on a map, professionals pay attention. Because history has shown that when those three align, gold is rarely far away. And once you know how to recognize that combination, you stop searching randomly and start predicting where gold must be. The map stops being a reference and becomes a forecast. And that is where the story continues. When geologists talk about alignment, they are not speaking in vague terms. They are referring to a specific convergence that has repeated itself across continents, across ages, and across nearly every major gold province ever documented. It is a pattern so reliable that when it appears on a geological map, attention shifts immediately. Budgets move, drill rigs follow, and history shows that gold often follows too. The first element in this convergence is a competent host rock, usually one that can fracture without collapsing. Quartz-rich rocks, metamorphosed volcanics, and certain intrusive margins excel at this. These rocks do not absorb stress quietly. They crack, and cracks are everything. Without fractures, gold-bearing fluids have nowhere to travel and nowhere to settle. On a map, these rocks appear as continuous units that persist over distance, not scattered patches. Their continuity matters because gold systems need space to develop. The second element is a structural engine. Faults, shear zones, fold hinges, and deep crustal breaks are not just accidents of geology. They are the plumbing system of the planet. These structures move heat, pressure, and fluid over immense distances. A geological map reveals their geometry, their orientation, and often their relative age. Gold favors long-lived structures, ones that were reactivated again and again over geological time. Each reactivation is another opportunity for gold to move and redeposit. Where these structures cut through the right host rock, the probability of mineralization increases sharply. But this alone is still not enough. Many regions have good rocks and strong faults and still contain no gold. That is because a third element must be present. The third element is a thermal or chemical driver. This is usually represented on a map by intrusive bodies, metamorphic gradients, or specific rock assemblages that indicate deep heat sources. Gold does not mobilize in cold systems. It requires energy. Magma rising from depth, or rocks undergoing intense metamorphism, release fluids capable of dissolving and transporting gold. These fluids are the carriers. Without them, gold remains locked and invisible. When these three elements overlap on a geological map, a very specific picture forms: a fracture-capable host rock, a major structure that can move fluids, and a heat source that can load those fluids with gold. This is the three rock and a structure convergence that professionals quietly look for. What makes this approach powerful is that it works before any gold is ever seen. It works even in places with no mining history. It works in forests, deserts, mountains, and private land where prospectors have never set foot. The map tells a story long before the ground does. Once this convergence is identified on a regional map, geologists narrow the focus. They move to more detailed maps, looking for secondary structures, bends and faults, changes in rock competency, and zones of alteration. Gold rarely deposits evenly along a structure. It prefers traps, places where pressure drops suddenly, where fractures widen, where chemistry shifts just enough for gold to fall out of solution. On the ground, these traps often appear subtle: a slight bend in a ridge, a change in rock color, a line of iron staining that follows no obvious pattern to the casual observer. But to someone who has already read the map, these features confirm what was predicted. Even placer gold follows this logic. Rivers do not create gold. They inherit it. When a drainage cuts through terrain where this three-element convergence exists upstream, gold enters the system. From there, physics takes over. Gold settles where energy drops, behind boulders, inside bedrock cracks, on the inside bends of rivers where flow slows and heavy material drops out. This means geological maps can predict placer gold just as effectively as hard rock deposits. By tracing river systems backward into favorable bedrock and structure, geologists can identify streams that must contain gold, even if only fine flakes. Conversely, rivers draining barren geology can be eliminated instantly, saving years of wasted effort. Modern technology has not replaced this thinking. It has amplified it. Remote sensing, geochemistry, and geophysics all layer on top of geological interpretation, but none of them function intelligently without it. The map remains the foundation. This is why the highest value gold discoveries are rarely accidental. They are the result of disciplined interpretation, of understanding how Earth behaves when pressure builds, when rocks break, and when fluids move. For those willing to learn this language, gold stops being a mystery and becomes a probability problem. You are no longer asking if gold might be present. You are assessing how likely it is and where it must have gone. And this changes everything. It changes where you walk, where you sample, where you pan, where you drill, and just as importantly, where you do not. The geological map does not promise gold, but when read correctly, it quietly removes most of the uncertainty. It narrows the world down to places that make sense. And when that three-element convergence appears clearly on the map, history suggests that gold is not far away, often closer than anyone expects. Gold is rarely random. It follows structure, pressure, heat, and time. What appears to be empty land often carries a history written deep below the surface, waiting to be interpreted. Geological maps do not guarantee discovery, but they quietly reduce chance and replace it with understanding. When you learn to read the signals the Earth leaves behind, every ridge, every river, and every rock formation begins to speak. And in that language, gold has always left clues for those trained to listen.